True or false? In order to lift a bucket of concrete, you must exert more force on the bucket than the bucket exerts on you. Oh, well. This one is about Newton's third law, which states that the force you exert on the bucket is equal and opposite to the force the bucket exerts on you. These two forces can never be different. Now, the net external force on the bucket, including gravity and the force that you're pulling on it, must be upward in order to get it to lift, but that's not what's being asked. 3 books are stacked on the floor in the back of a truck. So here's the truck, and there's the books. The top book has a mass of 1.5 kilograms. We'll call them 1, 2, and 3. The middle book has a mass of 2.0 kilograms, and the bottom book has a mass of 2.5 kilograms. Determine the magnitude of the static friction force that the bottom book exerts on the middle book if the truck is accelerating forwards at 1.6 meters per second squared. Assume none of the books slip relative to each other or to the floor of the truck. So there's no slipping. So that's fine. So what I'm going to do is define to be the top 2 books. Just go like this. And if you look at that, then you'll have the normal force on 2 upwards, and then the M1 plus M2 is the gravity acting downwards, and then the static friction force on 2 from 3. F2 is what we're looking for. Makes sense? So, and that's going to be the net force, F net in the x direction, if x is towards the right here, is at the mass of the object, which the system is m1 plus m2, times acceleration is equal to Fs. That's the only force there. So all we have to do is just solve this out. We've got 1.5 plus 2 times 1.6. 5.6. And that's Newton's. So the answer is D. 2 men pull on opposite ends of a string that has a spring scale in the middle. The man on the left pulls with a force of 500 newtons to the left, or this is 500 newtons. Yeah, that has to be the same, so this scale will read 500 newtons, and it is D. A mass of m equals 30 kilograms, I'm going to call it m, is suspended by 2 cables shown. What is the magnitude of the tension T2 in the right wire? So this is kind of the free body diagram for the point where the cables all connect to each other, if you can imagine that. So there's this is going to be mg down. And we need to balance all of those forces. So what I'll do is I'll define y to be up, x to be to the right, and we'll say that the net force in the x direction on that point is equal to 0. And that's equal to, if you look at this, it's going to be T2. We're going to call 10 degrees the theta 2, and we're going to call 55 degrees the theta 1, T1, theta 1. So T2 cosine of theta 2 minus T1 cosine of theta 1. And so what that means is that T2 cosine theta 2 equals T1 cosine theta 1. We'll call that equation 1. Also, the net force in the y direction is equal to 0, and that's going to be T1 sine of theta 1 plus T2 sine of theta 2. Those are the 2 upward components of the cables. And then the downward force on that point is just mg. And so that means, I guess we would say, T1 sine theta 1 plus T2 sine theta 2 equals mg. And call that equation 2. And we now have 2 equations and 2 unknowns, where the unknowns are T2 and T1. And we want to solve for T2. So what we're going to do is solve equation 1 for T1, and then plug it into T2. Plug it into equation 2. So 1 implies that T1 equals T2 cos theta 2 divided by cos theta 1. We'll plug that into 2. So we get that T2 cos theta 2 sine theta 1 divided by cos theta 1 equals plus T2 sine theta 2 equals mg. And now it's all in terms of T2, so pull out the T2. We say T2 equals mg divided by, and then there's all this cosine stuff. Cosine theta 2 sine theta 1 divided by cosine theta 1 plus sine theta 2. So now we have to carefully plug all this stuff in. You've got 30 times 9.8 divided by, let's just actually work out what this is, divided by 10 cosine times 55 sine divided by 55 cosine equals 1.4, and then plus 10 sine equals 1.58. So this is divided by 1.5801 times 30 times 9.8 equals 186 newtons, and that is closest to B, 190. Two blocks are stacked on top of each other on the floor of an elevator. The elevator is moving downward, V down, at an increasing speed, so the acceleration is down. The magnitude of the force of the bottom block on the top block is blank the magnitude of the force of the earth on the top block. So we just draw a force diagram. This is the force of the earth on, we'll call the top one, I guess, 1, and then this 2 on 1. And then this, it's only in contact with one other object, and that's 2. That's the force of 2 on 1. And since the whole thing is accelerating downwards, we know that there must be an unbalanced force in the downward direction, so the force of E on 1 has to be greater than the force of 2 on 1 in magnitude. And the force of the bottom block and the top block is, so that's actually, this is less than, right? So C. If you stand on a trampoline, the surface of the trampoline sinks down under your feet as it supports your weight. If you stand on a hard stone floor, according to the laws of physics, what happens? And so this is all about these self-adjusting forces, normal force and static friction and tension. So these are your textbook talks a lot about the microscopic little springs between the atoms. And so the reason the normal force self-adjusts when you stand on even the hardest floor is that the floor must be sinking just a little bit and compressing those springs. So the surface, the answer I'm looking for is A. The surface of the floor must always sink down a tiny bit under your feet as it supports your weight, so that it knows how much to push up on you with. A book rests on top of a table. A downward gravitational force of magnitude 5 newtons is exerted on the book by the earth. Okay. The reaction to this force, as described by Newton's third law, is a force of magnitude 5 newtons exerted on the... Okay, so this, let's find the reaction force. So this is the force of Earth on book. So if this is the old Earth down here, then Newton's third law states that must be equal and opposite to the force of the book on the Earth. So exerted on the Earth by the book, and its direction is up. So Earth, book, upward. I choose A. A steel ball of mass 0.35 kilograms is released from rest at a height 1.55 meters above a soft foam mat. So V0 equals 0. When the ball hits the mat, it then sinks a distance of 4.51 centimeters before it stops. Okay, so the first thing that happens is it goes some distance y1, which equals the 1.55 meters. And then it sinks some distance y2, which equals, in SI units, meters, you got to divide by 100, so you'll get 451 meters. Okay, so during this first segment of motion, A sub y equals G, 9.8. But then, for here, it's going to stop. I guess V2 is going to be 0, right? And then there's V1 down here. So V1 will be the initial of this second motion, and and the final of the first segment of motion. So I think, again, we don't really care about the times here, so we're going to keep on using, it looks like it's a good thing I wrote this equation on my aid sheet, equation 2.7. So V1 squared minus V0 squared is going to be equal to 2 times G times Y1. And so we can actually, this is 0, we can say right there that V1 squared is equal to 2 times G times Y1. Then this is going to stop, and it's the same kind of thing. We're going to assume that there's an acceleration upward, and let's find that, I guess. So we have V2, we can use kinematics to find that. V2 squared minus V1 squared is equal to 2 times A times Y2. What we're trying to actually find. And in this case, this is the 0 one. So A is going to be equal to negative V1 squared divided by Y2. And in fact, I even have that. I can just take this, so I already solved for this, and plug it into here. So the acceleration is equal to negative 2 times G times Y1. Oh, I forgot a 2 here, divided by 2 times Y2. And the 2's cancel, and you get the acceleration is negative G times Y1 over Y2. Okay, so that's the acceleration. Now we're asked about the force. So the force diagram, while slowing down, and I think what I've done here is I've defined plus y is down, by the way. So the force diagram while it's slowing down is going to be, there's this force up, which I think is what you're trying to find. And then you've got mass downwards, force of gravity downwards, which is m times g. And remember, plus y is down. And there's some acceleration in the y direction that we found here. So I would say that the sum of all the forces in the y direction is equal to the mass times a sub y. And so that's going to be, I guess, actually mg, because that's positive now, minus f is equal to m a sub y. Solving that out, I think you find that the force is equal to mg minus m a sub y. And then we have a sub y from here. So we can plug that into here. It's going to be the mass times g. And then minus a minus, you're going to end up with a plus of the mass times g times y1 over y2. And so they both have mass in it, so it's going to, and they both have g, so it's mg times 1 plus y1 over y2. And plugging in all the numbers, we have 0.35 kilograms times 1 plus, it fell 1.55 meters, and then stopped over 0.0451 meters, 0.35 times open parentheses 1 plus, another open parentheses, 1.55 divided by 0.0451, close parentheses, equals, and I got 12.4. Oh, I forgot the times by g. Times 9.8. 121. 9.8. Don't forget to do m times g, right? Which is 121 newtons. A low friction cart of mass 0.54 kilograms is on an aluminum track that is tilted at an angle of theta is 25 degrees above the horizontal. The cart is connected by a string going over a pulley to a hanging object with mass m equals 0.062 kilograms. What is the acceleration of the hanging object? Right. So what I'm going to do is define plus x is down for this one, and then x is up for this one, and y is up for this one. And we did this quite similar in class, but the M force diagram is going to have a normal force that's in the y direction. It's going to have a tension force that's in the x direction, and it's going to have a gravity force, capital Mg, that has two components. It has a negative x component, negative Fgx, and it has a negative y component, negative Fgy. And since it's not accelerating in the y direction, you can right there tell that normal force minus capital Mg cos theta equals 0. So the normal force on the cart, which I don't think matters actually, is equal to Mg cos theta. But then the sum of the forces in the x direction, which is equal to its mass times its acceleration, a, is going to be equal to tension minus mg sine theta. Okay, so that's one equation. And then for this equation, for this little m, you've got just tension going up and little mg going down. And again, you've defined plus x down, and the acceleration's down. So the little mass times acceleration is mg minus the t. So what we can do to solve this out is we're trying to find acceleration. And so we want to eliminate t. So t here is equal to ma plus mg, all lowercase. I'm going to take this and plug it into my second equation there to get a. So I've got capital M times a is equal to little m a plus little m g minus capital M g sine theta. And I just have to collect all my terms with a on one side of the equation. So I've got the acceleration times capital M plus little m is equal to mg minus capital M g sine theta. And then so acceleration is just little mg minus capital M g sine theta, all divided by capital M plus m. So it's going to be the hanging mass is 0.062 times 9.8 minus 0.54 times 9.8 times sine of 25 degrees, all divided by 0.54 plus 0.062. So 0.062 times 9.8 equals minus, open parentheses, 0.54 times 9.8 times 25 sine equals, and that, and then divided by, open parentheses, 0.54 plus 0.062. So I get negative 2.7. So what the heck does that mean? Negative a is equal to negative 2.7 meters per second squared. And this is, by the way, in this x direction that I've defined. So what this means is that the cart goes in the negative x direction and the mass goes in the negative x direction. And we defined for the hanging mass, positive x is down, so that means the hanging mass accelerates at 2.7 meters per second squared upward.